So in the last couple slides, I simply want to compare sort of what we've just stated about ionic compounds with molecular compounds, with covalent bonding, and then briefly talk about sort of the simplest sort of basic model for metallic bonding. So when we think about covalent bonding, and what we've kind of talked about with Lewis theory, right, is again, Lewis theory predicts that these molecules form with covalent bonding, that we form individual molecules when we form when we have covalent bonding involved. Now, because we don't have to break these bonds, right? Because we don't break down molecules when we boil or melt a solid, a molecular solid. So like when we melt ice, right, we don't break down the water molecules. We just simply separate the water molecules from each other. So this involves breaking relatively weak attractions between the molecules, what we will eventually call intermolecular forces. So the key is we're breaking attractions between the molecules, not the bonds between the atoms. So this is going to take much less energy, and so we would expect much lower melting and boiling points compared to ionic salts. And this is generally true, right? Melting points of molecular compounds are below 300 degrees, and most are well below 300 degrees. And as a result, we can find molecular compounds that exist in all three states of matter at room temperature. We have ones that are solids, which have higher on the higher end of the melting point. We have liquids, which are sort of intermediate, and we have things that have quite low boiling points, well below room temperature, which exist as a gas already at room temperature. Now, if we sort of visualize this, right, and we have a molecular compound here, this is pentane, right, C5H12, right, so we have a solution of pentane, and we're sort of heating it here a little bit, and we start to get evaporation. And the key here is, right, what we are doing is breaking these relatively weak intermolecular forces represented by the dashed lines here, and not the bonds within the molecule, right? The so-called covalent bonds, which are going to be, on par with ionic bonds, right? So the fact that we don't have to break those bonds and we only have to break the weaker leads to these lower boiling and melting points. Okay, so now let's talk about metallic bonding. So metallic bonds can be envisioned with what's called a sea of electron model. So basically what we look at is ionization energies of metals, right? So we know ionization energies of metals are low. Right? This means they lose electrons easily. Now, if we imagine a bunch of metal atoms, though, they want to lose electrons, but there's nothing to gain them, right? If we combine them with a non-metal, of course, they're going to react and they're going to form an ionic compound. But what if we just have metal ions? Well, what we think is that in sort of a simplified way of looking at it, that the metal atoms all lose their electron or become cations. So we actually form a bunch of metal cations, but those electrons are not directly shared with any other metal atom, but they're put into sort of a pool, if you will. And so this is what we think of as the sea of electrons that surround these metal cations. So what we envision is, if you will, a bunch of metal cation islands, right, surrounded by a sea of negatively charged electrons. So we got cation islands in a sea of electrons. Now, what this allows is movement of those electrons. So they can hop from one metal cation to another, right? They can island hop, if you will. And this results in what we call electron delocalization, which allows conductivity. So this metal is very consistent, or this model is very consistent with what we experience with metals, and some of their basic properties, chief among them being the ability to conduct electricity, right? So just like we see conductivity in molten ionic compounds or solutions of ionic compounds where we have free-moving ions, it's the same thing here. We have ions and we have the ability of electrons to move, negative charges to move through from positive charge to positive charge. It allows conduction of electricity. Now, the actual bonding, right, we think results from the attraction between the positive cations and the negative electrons. So having these positive cations, these electrons, these attractions are what provide the bonds between the metal cations. So the bonding is, again, electrostatic in nature, but in this case, it's the attraction between the metal positive ions and the negatively charged electrons. All right, so that wraps up our initial look at bonding theories, focusing on Lewis structure. And we will turn our attention back to Lewis structure in Chapter 11 and expand upon it into theories that build on Lewis structure, and then looking at some alternative theories to Lewis structure.